begin. So first off, I want to correct a mistake from last lecture. So I think the mistake was in the second KVL loop equation, the lower loop equation. I think the direction of the currents were different last time, was it? But we'll follow this direction, it wouldn't make a difference. But if I write the KVL for the bottom loop, I think the last time the mistake was in the arm resistor inductor drop. Instead of subtracting the drop, I added the drop, if you check those equations again. But equation will be 0 minus VDC by 2, this drop. So there is a voltage of VL produced here, the total lower arm voltage, so 0 minus VDC by 2, and then plus VL, 0 minus VDC by 2 minus VL, and then the current is flowing this way, so the arm inductor drop will be like that. So I need to minus of this drop will be plus IL R arm plus L arm DIL by dt. 0 minus VDC by 2 plus VL plus this drop equals V out. And then KVL for upper arm will be 0 minus VDC by 2. So this VDC by 2, so I have plus VDC by 2, and this voltage is VU, so minus VU, and the current is flowing like that. So arm resistor inductor drop will be like that. So plus IU R arm plus L arm D IU by dt. So 0 plus VDC by 2 minus VU plus this drop equals VU. So 1 and 2, and then if I add 1 plus 2, I get VC by 2's cancel out, get VL minus VU plus R arm plus L arm d by dt of IL plus IU. IL plus IU, and IL plus IU is output current. So this should be equal to 2 VO. So we get VL minus VU by 2 plus R arm by 2 times IL plus L arm by 2 times d IL by dt equals VO. So there was a mistake last time. The mistake was in the direction of the drop of the arm inductor resistor in the bottom loop, if you check. So last time, instead of adding this drop, I subtracted the drop. So this is the right equation. So output voltage here, this is VO, this point is VO, and that voltage is given by VL minus VU by 2 plus this equation. There is an easier way to come up with this equation. I can redraw this circuit like this. I have VDC over 2 and I have plus minus VU, and then I have this is ground, and then I have plus minus VL, and I have an IL flowing into that node, and I need to find the voltage here. So suppose I run this circuit in experiment or simulation, and I measure, I know what VU is and VL is because that's under my control, and then suppose I measure IL, and then I wanted to find out this point's voltage VO. What would I do? I would apply superposition, right? So I would find the effect of VU on this node. That will be, I will open this circuit, open this current source, short this voltage source, short this voltage source. So as effect of these two voltages at this point, the voltage here will be minus VU by 2, because these arm inductors are the same. So by potential divider you get this net voltage times half at this point, and then plus you get VL over 2, and then you short these two sources and find the effect of that current. You have arm inductors and resistors in parallel to each other, so you have plus IL times plus IL times R arm by 2 plus L arm by 2 d by dt. Is that clear? So we get this equation, and so basically again VO is just the average of this voltage looking up there and this voltage looking down there approximately, and then the effect of IL due to the arm inductors and resistors. So this part is done, and then we need to look at the waveforms for VU, VO and VL. So as you notice, the effect of the circulating current cancels out at VO, because circulating current causes a drop in this voltage direction, and here it causes this voltage. And if the voltages are same, the effect is cancelled at VO, looking up like that and looking down like that. Okay. Look at the output voltage waveform. It looks like this. So we have 4 submodules here, right? We have 4 submodules in top arm, 4 submodules in bottom arm. So how many voltage levels do you expect to see at the output? Last time we had how many modules? We had 2 modules and we had 3 voltage levels, right? So the output will see VDC minus 1 VC, VDC minus 2 VC, and VDC by 2 itself. So you get, do you remember? See, when we had so I'll rub these equations out. And last time we had VO, looking at the upper loop, we had VDC over 2 minus 2 VC two modules are inserted, VDC over 2 minus VC, one module inserted, and VDC over 2 minus 0, two modules bypassed, right? So we had we know 2 VC is VDC, so this will result in minus VDC over 2 when two modules are inserted, 0 when one module is inserted, and VDC over 2 when two are bypassed. So at the output voltage we expect to see this type of a waveform. So this is 0, or we expect to see a PWM version of it. So if this is a sine wave we want to synthesize, we expect to see PWM version of it till here. PWM, let me draw it again. I'll rub this off. So if I want to synthesize this sine wave, I can do that, or I can do right, I can do this. So I have a plus VDC over 2, 0 or minus VDC over 2. Similarly, VDC over 2, 0 minus VDC over 2. So how many levels do you see in the output? You see 1, 2, 3 levels. So similarly with 4 submodules, how many levels would you see? So we'll rub this off now. So we know 4 VC is VDC, right? 4 VC is VDC, and then for output voltage we see VDC over 2 minus 4 VC, VDC over 2 minus 3 VC, VDC over 2 minus 2 VC, VDC over 2 minus VC, VDC over 2 itself. What will this be? This will be minus VDC over 2. This will be, let's give numbers to VDC. So let's give the same number that we have in simulation. Our VDC here is 2500 plus 2500, 5000 volts, okay? So this is 5000 volts. So what is VC? It's 1250 volts, right? 4 VC is VDC, VDC is 5000 volts, so VC is 1250 volts. So this should be minus VDC over 2, which is minus 2500. What will this be? This will be 5000 minus 3 times 1250 is minus 1250, right? VDC over 2 is 2500, yes.
You did 5000 minus?
2500 minus 5000 is minus 2500.
Correct, but the line below it, you just wrote 5000.
Oh, okay. Sorry. 2500, yes, thanks. Minus 3 times VC is how much? 4 times VC is 5000, so 3 times VC is 5000 minus 1250. So I can write this as 5000 minus 1250. So how much is this? Minus 2500 minus 1250 is minus 3250. Minus 2500.
Minus 1250 is what it should be.
Yes. So this is minus 1250. And then what is this? 2500 minus 2 times Vc is 2500, which is 0. VDC minus Vc is, thank you, and this is just VDC over 2, that is 2500. Okay, so in the output voltage, what all levels will you see? You will see minus 2500, minus 1250, 0, 1250, and 2500. And it goes like that. So this is 0. So 1, 2, 3, 4, 5 levels. What do you see in the output voltage actually here? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 9 levels. How did that happen? So we also need to look at the lower arm. So the output voltage is approximately VL minus VU by 2. So if there are say all modules inserted here and no module inserted here, do you follow? See, if I insert all 4 modules in the upper arm, I get how much? Minus 2500 volts, right? Similarly, if I bypass all 4 modules in the lower arm, I again get minus 2500 volts, right? Minus VDC by 2 appears as the output. Do you follow? If I bypass all this, minus 2500 appears as the output, right? So when we have the following cases, so VO is this, I will rub this off. So in the upper arm I have 4 module inserted, so I am writing upper comma lower here. So 4 comma 0 I get minus VDC by 2. Similarly, upper comma lower equals 3 comma 1 I get minus 1250. So say this is minus 2500, minus 1250. So upper comma lower equals 2 comma 2 I get 0 volts. Upper comma lower equals 1 comma 3 I get plus 1250 volts. And then upper comma lower equals 0 comma 4 I get plus 2500 volts. These are the same levels that you would expect here. But what will happen when upper comma lower equals 4 comma 1 or upper comma lower equals 3 comma 2? So 2000, 2500. Let's look at the 3. Okay, when 4 modules are inserted in upper, I get minus 2500 volts. When 1 module is inserted in lower, I get minus. So this is average of what? When 4 modules are inserted, I get minus 2500 volts plus when 1 module is inserted in lower arm, I get minus 1250 volts, and the average of that will be my voltage. But maybe this case doesn't happen in the PWM scheme that we implement, but let's look at 3 comma 2. What is 3 comma 2? I get minus 1250 volts plus, if 2 modules are inserted in lower arm, I get 0 volts by 2. That happens here. So this is approximately minus 625 volts. So that happens here. Okay, and then upper comma lower equals 3 2. So how about 3 comma 0? Does that happen? That won't happen. But 3 comma 3 should happen. 3 comma 3 it's minus 1250 volts plus. What will happen if it is 3 minus 1250? 2 is fine. 1 module here. So plus 1250. Plus 1250 by 2, that's again 0 volts. So what do we need to produce? We need to, this we already have. We need to produce this voltage. We have this. We have this. We have 2500. What is this voltage? It's the average of 1250 and 2500. So how do we produce average of upper comma lower? How do we produce average of minus 2500 volts plus minus 1250? Can you tell me how many modules should I insert in upper, how many in lower? For upper, we know for minus 2500 we need 4 modules, right? So I have 4 there. For minus 1250 volts in lower, how much do I need? I think I need 1 module, right? If I have 1 module in lower arm, see if I have 1 module here, I have how much? Minus 2500. So minus 2500. So the VL minus, so it goes like this, right? 0 minus VDC by 2 plus VL, like that. So minus 2500. So remember the KVL equation 2 that I wrote before, if you look at that, 0 minus 2500 plus VL. So how much do I need? I need minus 1250 volts. So plus, what VL will give me plus 1250 volts? 1 module, right? 1 module plus 1250 volts. So it's here. Here. This is minus 1250 volts, and that is here. Minus 1250 volts, 1 module. So 4 comma 1 will give me average of these two. It will be how much? Somewhere here. Somewhere here. That's 0, 5, 4, 3, 1, 7, 2, 5. Is that right? Okay. So then now how many levels in output voltage can we have with n number of modules per arm? Number of modules per arm. How many output voltage levels can we have?
2n plus 1.
Thank you. 2n plus 1. Number of levels in output voltage. All right. Yes. So then, what is the use of all these levels? How does it help us? What is the use of having more number of levels that we can produce with an inverter?
You get a better sine wave.
Yes, I get a better sine wave because if I have this sine, if I rub this off, if I want to produce this sine wave, if I only have 0 and this voltage level, I need to switch between these two levels only to produce the average. But if I have multiple levels in between, I can switch between those two levels, right? Because those are my closest levels to the average voltage that I want. So numerically, how can we quantify the quality of waveform? You can do frequency domain analysis. You can look at the frequency domain components of the voltage that you synthesize at your inverter output. But a simple way, even more straightforward way will be to suppose you have this sine wave and you split it into say 200 intervals and produce 200 different average voltages. Why 200 intervals? Because my carrier frequency, if this is a 50 hertz waveform, and if my carrier triangular carrier is 10,000 hertz, how many intervals will I split it into? 200 intervals, right? I will produce 200 different averages because 10,000 by 50 is 200. So what will I do? I will take one bit here, and the next bit here, and the next bit here, and the next bit here, next bit here, and produce a different average at each of these 200 intervals. That is how we produce a sine wave. Now let's look at the accumulation of the RMS voltage error along these 200 intervals. So what will be the RMS voltage error? RMS error will be, see, I suppose my converter, V converter can produce some number of levels. Let that level be denoted by a voltage V converter, and the average I want to synthesize at different points is VO. Let's call this whole waveform VO. VO varies like a sine wave, and this for quantity varies also. So V converter is the voltage level I can produce at any instant. So this, the whole square. So RMS is root mean squared. So I have done a square, and then I need to sum it up over 200 intervals, and then I need to take an average of this, and then I take a square root. So if V converter is closer to VO at every one of these 200 intervals, I get a low RMS error, right? So VO keeps varying like this. So if I have V converter nearby VO at every one of those 200 intervals, I get a lower RMS error. So that's why more number of levels leads to purer sine wave. Yeah, so this is something, and then I will rub this off, and then so we have looked at VO here. Let's look at VU. I think it is running again. I can stop it here. No, yeah, you stop it here. So we looked at VO. Let's look at VU. See, this is VU. It is a net voltage created by some of submodules. So if I look at that, what does it show me? Let me see. Time, auto, apply. Okay. So how many levels do I have in VU? I have 0. I have 1250. I have 2500. This is VU, okay? It's not VO. This is VO. So VU will be what? VU will be 4 times VC, which is 5000, right? 5000 and 3 times VC, 2 times VC, 1 times VC, and no VC, VU. So VO minus this VU is output voltage. And look at what is happening here. There is PWM between levels. See, there is PWM between 4 VC and 3 VC to produce a sine wave in between those two voltage levels there. See, what I mean is VU should look like what? Should look like this, right? Around an average of VDC by 2. Because VDC by 2 minus VU is VO, which we saw last time. So VU should look like this. So what is happening in this interval? Which portion of VU do you think this interval corresponds to? 5003 VC. It should correspond to this interval, right? Yes. So next it will be 3 times. So 4 and 3, 3 and 2, like that. 2 and 1, and 1 and 0. That's what's happening here. Okay, 4 and 3, 2 and 1 and 0. So that's VU, and then let's look at VL here. VL will be just in the same phase relation as output voltage. So same phase relation as output voltage, and again we have 4 levels. So when it is 5000, we get output voltage at 2500 because it's VL minus VDC by 2 at the lower arm. So then, so we've looked at this, we have looked at this submodule output voltage equation. So I'll rub all this off. I'll rub these things off maybe. So, we need to synthesize a VU like this, which is a sine wave. In order to produce this sine wave average, what is VU composed of? VU is sum of submodule output average voltages. So that's a V submodule average over N. N is a number of submodules in an arm. So VU should be a sine wave. It follows that V submodule average should also be a sine wave, only 1 by N times this VU. So what I mean is this can be written as all submodule averages are the same. Let's say they are the same. If they are not the same, then one of the submodule which produce higher average voltage will absorb higher power, which means that capacitor will be having higher voltage. We don't want unequal voltage. So let's say all submodule average voltages are the same. So this can be written as N times V submodule average. So each V submodule, so this is the V submodule average voltage. So the thing to be noted here is that submodule average is taken at the output of the half bridge with respect to bottom of the half bridge. So V submodule average, if it is some M times Vc, what do you think M is? Because submodule average is taken to the bottom of the half bridge. V submodule average cannot go negative, right? Because the most negative, with respect to this point, the submodule average can only be 0 at the minimum. What I mean is M times Vc, if you write it as M times Vc, then M should be 0.5 plus Ma sin omega t. So submodule average will look like this. Around Vc over 2, you will have a sine wave like that. Since I drew it for the upper submodule, I drew it in opposite phase to output voltage. So this may not be sin omega t, this may be sin omega t plus 180 degree for the upper submodule. Okay. So that's so the modulating signal to form submodule average, where modulating signal is M times Vc is given by this. So submodule output voltage equation is that. This equation is useful for us to find out how the circulating current is produced. So we can, I'll rub this off, but you can keep it in mind. And then, so we did this, and then we need to look at power absorbed by upper arm. Yes. So I'll rub this off. Okay. VU, let's say. So VU waveform is a sine wave around an average of VDC over 2, and then we also know that VO is approximately VL minus VU by 2, and let's say VO is VP sin omega t. Okay. So then what will be VU now? VU will be what? So PU is VU times IU. Now IU is shown like that. So maybe we can take it as minus IU. Yeah, maybe that's better. The power absorbed by the upper arm, okay? Power absorbed by the upper arm. So VU is what? VU is VDC over 2 plus VP sin omega t times minus IU is what? IU I had written, IU was what? IU was minus I circulating plus IL over 2, right? IU was this, plus IL over 2 minus I circulating. I circulating in turn consists of I DC and all even order harmonics. How this comes about and how this comes about, I will tell you. In fact, how this comes about is almost clear from this. And why should there be an IDC? If there is an output power here, that power should be given by the DC link. DC link gives power by IDC. So IDC flows through the leg back to the source. So there is an IDC clearly, but how this comes about we need to see. So what is IU? IU is minus of this. So I have, let's ignore this part now. Let's assume this is 0. We don't know. We don't know if it's but let's see. Let's think that it is 0. We only have IDC. In that case, minus IU will be minus IDC minus. So we need minus IU, right? Okay. So what is minus IU? Minus IU is IDC minus IL by 2. Okay. What is IL? Let's say IL is some IP sin omega t plus phi. That is a phase shift of the output current of phi. So I have here minus IU will be IDC minus IP sin omega t plus phi. So what is this? Why am I saying all this? I want to say that there is an IDC and we want to find out how much that IDC is and how that IDC affects capacitor voltage waveforms. What will happen if IDC is not there to the capacitor voltages? That is our aim. Maybe I will show you how capacitor voltage looks like before solving that. Where is capacitor voltage? It is here. So this is arm current that I have taken out, and this is okay. What is this? This is VMO17. VMO17 is right here, I think. See VMO17. So that is the first submodule's capacitor voltage in the upper arm. Okay. So we are looking at the arm current, upper arm current, and first arm's first submodule capacitor voltage. So if you look at that, okay, this is the capacitor voltage and this is the arm current. So what do you see in the arm current? What do you observe? What is the frequency first of all? What is the frequency, dominant frequency in the arm current? See, for 60 Hertz, what will be one cycle's time? Approximately 20 milliseconds, right? So what is the time for one cycle here? Is it approximately 20 milliseconds? It looks like there is a fundamental component in arm current. But what other thing do you observe? Is it symmetrical? About is the positive peak the same as negative peak? Can you see the numbers? Like, should I zoom in or something?
I can't see it very well. Yeah, you can come back here if you want. It's visible.
Yeah. Can you see? So what do you see? It's not symmetrical, right? The positive peak and negative peak are not the same. So what does that mean? It has an IDC component. It has an IDC component. How does the IDC component help us? It in fact helps us in maintaining the capacitor voltage at an equilibrium. Okay, so from this curve, see, okay, let's see. If the arm current is positive, what happens to the capacitor voltage? Is it increasing or decreasing? It's decreasing, right? So let's look at the direction of arm current in simulation. It is out of the arm, like positive is here. So if you look at the simulation file, it is out of the arm. So it's out of the arm. Arm current is the same polarity as this. So if the capacitor was inserted and arm current was like that, the arm current would flow like this, right? That means capacitor should discharge, right? And what do you see here? If the arm current is positive, capacitor is discharging, and then it remains constant. It remains constant, almost constant, even when current is positive. Why does it remain constant? We'll have to see. And then when arm current is negative, capacitor voltage is increasing, which is okay, right? When arm current is negative, current should be flowing in like that, and if module is inserted, the capacitor charges. Okay, so when it is positive, the capacitor voltage increases. When it is negative, the capacitor voltage increases, and then when it crosses the positive, it again decreases. And then here what happens? It is positive, and positive or negative doesn't matter. The capacitor voltage is staying constant here. Why is it stay constant here? We have to see. And then when it is negative again, see at this point it is still negative and capacitor voltage is increasing again. So note the behavior. Okay, you have noted the behavior. Now let's solve this, and we know there is an IDC in arm current, and I am telling you that IDC is important for capacitor voltage equilibrium, charge equilibrium, otherwise it will keep increasing or keep decreasing. The reason for it will be clear soon, but if you solve this, we have VDC over 2 times IDC minus VDC over 2. And keep thinking why capacitor voltage stays constant, okay, during some portions. So IP sine omega t plus phi, VDC IDC, VDC by 2, right, and then plus 4 terms, we get 4 terms, VP IDC sine omega t, and the last term. So I have minus VP IP sin omega t times sin omega t plus phi. I get 2 omega component and a DC component. The DC component will be Vp Ip by 2 cos phi. Can you quickly calculate what this is? Sin omega t times sin omega t plus phi. What is sin A times sin B? Sin A times sin B is what? It is cos A minus B plus cos or minus cos A plus B by 2, right? So I get Vp Ip by 2, that by 2 is here, and if I do A minus B, omega t minus cos phi will be what? Will be cos of minus phi, which is cos phi. Okay, and then I will get what? I will get a plus term, right? This net thing is minus, so the plus term has become minus. Minus term will become plus. Okay, then I get plus Vp Ip by 2 cos 2 omega t plus phi. Okay, How many terms do we have? 1, 2, 3, 4, 5 terms. This was one term, we expanded it. All right. Now, for the, if the upper arm absorbs a net DC power, the capacitor voltages keep increasing. If the upper arm gives out a net DC power, the capacitor voltage keeps decreasing. So the net DC power absorbed by upper arm should be 0. What I mean is, the power given by upper arm to the output should be got back from the DC link to the upper arm through the DC link current. So how that manifests here is the sum of this term, the sum of this term and the sum of this term should be 0. Okay. So then we can solve for that and get what IDC is. So when I said IU is IL by 2 and IL also has IL by 2 component here. So I said IL is I circulating plus IL by 2. IL by 2. So why does IL split equally between upper and lower arm? Because VU and VL looking up like that has the same average voltage, which is output voltage Vp sin omega t, right? So then IL splits equally between upper and lower arm on an average. Instantaneously the upper arm and lower arm don't take equal currents from here because we saw that in the output voltage it was created by average, right? When it was average, the net voltage created by VU and VL may not be same to create an in-between voltage. So for that duration maybe current increases, for the next duration current decreases, but on average IL by 2 splits equally between upper and lower arm. Okay. And we also see there is a fundamental frequency component and 2 omega frequency component absorbed by the upper arm, which will in turn lead to fundamental frequency capacitor voltage ripple and 2 omega capacitor voltage ripple. Yeah, we know that so VU will have the fundamental frequency component power and 2 omega frequency component power, but that still doesn't tell us why there is a circulating current exactly. We will get to that. So we have that equation, and then what? So power absorbed. So capacitor voltage waveforms are shown. Did you find out the answer for why capacitor voltage remain constant during some portions? We will know the answer by looking at here. So what I did here was the upper arm current, the same submodule capacitor voltage, and another graph is a switching pulse to the submodule, the same submodule. Now let's open this. We open that, and then if I look at that, so submodule, this is the start of the simulation, so it will settle to a constant average value, but let's look at why it remained constant during some portions. Okay, I will pan this. This is the capacitor voltage. Look at some portion here. Okay. Arm current is negative, which means capacitor voltage rises. Arm current is positive, capacitor voltage falls, and it remains constant here. What is happening here that is making it constant? if I zoom in on here, I see that the module is barely inserted during the time when capacitor voltage is constant. Why is it barely inserted? Because maybe we want to produce a low voltage for VU during that time. Maybe VU at that time was around 0. Do you get what I see, what I mean?
What do you mean by badly inserted? You just mean
Barely inserted.
barely.
It means it's not inserted at all. So what I say is, if VU was this and this was VDC by 2, it's 0 here, right? So when it is 0 here, we want to produce a very low voltage. So that means it will switch between one module and 0 module. So when no modules are inserted, at that time we don't have any change in capacitor voltage charge. So that's what's happening when the modules are not inserted. We don't have any capacitor voltage charge. So we looked at capacitor voltage waveforms here. We looked at IDC and origin of second harmonic. So if you look at this file here and capacitor voltage waveforms, these are the capacitor voltage waveforms. So 4 submodules in top arm, and we have 4 submodule capacitor voltages. So the submodule capacitor voltage will have 3 frequency components. One is DC, one is second harmonic, and one is fundamental frequency component. Okay. Let's look at how these 3 components are produced. Okay. The capacitor voltage profile. Okay. Okay, let's look at the power absorbed by one of the submodules. So it is output voltage at the submodule times the current through it. Okay. Let's look at the interaction of the submodule output voltage with this component. So that will be so this times Vc times Ip sin omega t plus phi power by submodule so whatever power is absorbed at the output of the submodule should be from the input, the DC link too. So DC link power and the output power of submodule should match at every frequency component. So I have 0.5 Vc times Ip sin omega t plus phi. So this creates a fundamental frequency component here at the submodule capacitor voltage. So no, before that, let's assume Vc is completely constant. Okay, this is Vc. Let's say that Vc is a DC voltage. The capacitor voltage has only a DC component. It's a clean DC source. If you assume that, then for this frequency, so this is the power at the output of the submodule. So modulation index times Vc times the current. We know this current flows through the submodule. This current causes the power to be absorbed at the output of the submodule, because Ip sin omega t flows through upper arm and lower arm. Okay. So for this frequency power to show up at the submodule capacitor, if it was purely DC, what should we need? We need a fundamental frequency component at the DC link, right? We need a fundamental frequency component at the DC link, and that fundamental frequency component of current at the DC link of each submodule creates a fundamental component of voltage too. There's another way to look at it, but this is one way, and then let's look at So we did 0.5 Vc times this, and then let's look at interaction of these two. So I have plus Ma times Vc times Ip times same thing, right? This is minus, so yeah, so minus, so it's the same thing. So Ip, so by 2 times minus cos phi plus plus cos 2 omega t plus phi. So this is a DC component of power, and there is a 2 omega component of power absorbed by the submodule output. It's very simple because we have a sin omega t component in modulating signal multiplied by a constant Vc. Now we have assumed Vc is a clean DC source, constant. So that with the sinusoidal current will produce a 2 omega component at the submodule output power. In order for 2 omega component of power to be reflected at a clean DC link here, clean DC bus submodule capacitor voltage, what do we need? We need a 2 omega current, right? Because DC voltage times 2 omega current produces the same 2 omega power. So if you have a 2 omega current at the DC at the submodule capacitor, we will have a 2 omega voltage too. Now let's assume that Vc is not DC anymore. We know that there should be a 2 omega voltage component, and we also know that there should be a omega voltage component, fundamental frequency voltage component. Okay, let's include all that. So I'll rub this off. So from clean DC, we have come to the conclusion that Vc should have Vc average, which is DC, plus Vc omega plus Vc 2 omega. Three components we know it has. Now so I told you that the circulating current contains even harmonics. Let's see how second harmonic is produced first. So Vc 2 omega is there because of power balance. Now modulating signal is what? 0.5 plus Ma sin omega t plus 180. So what will be the submodule output voltage now? It will be 0.5 plus Ma, let me call that Ma omega, Ma sin omega t plus phi, times Vc average plus Vc omega plus Vc 2 omega. So this 0.5 times Vc 2 omega creates a average 2 omega component at the submodule output, and that adds up to this. What's more interesting is 2 omega output voltage component at submodule is of the same polarity in the lower arms. Do you know why? Because we have Ma sin omega t plus 180, instead of that we have Ma sin omega t in the lower arm. We know why. And then power absorb, and then so what I should have done is the power absorbed by the submodule at its output should be minus Iu, because this is plus here, should have been minus Iu, because plus minus I used Iu, I used IL by 2 component in Iu, it should have been minus Iu. So this should have been minus, and this should have been plus, and this should have been minus. So what I mean to say is, if this is plus 180 degree, this is minus, but in IL by 2 it is the same polarity. It is not minus Ip sin omega t that makes power to be absorbed. It is Ip sin omega t that makes power to be absorbed, and modulating signal is also not 180 degree phase shifted. So the 2 omega component ripple in the submodule capacitor are of the same phase relationship in upper and lower arms. That's what I mean. See, this is P submodule in upper arm. P submodule in lower arm will be what? Will be 0.5 plus Ma sin omega t times Vc times, instead of minus Ip sin omega t, I have Ip sin omega t plus phi. So that will create the same 2 omega component ripple at the same phase relationship 2 omega component ripple at the upper and lower arms, and so 0.5 times Vc 2 omega has the same phase relationship everywhere, and then the sum of the 2 omega voltage at the output of submodules divided by the impedance of the arm inductor and resistor creates a 2 omega circulating current. Okay. Now that's not all, we have more even harmonics at the output. In fact, we have, instead of fundamental, we have other odd harmonics at the output too. So if you look at MA omega times Vc 2 omega, what do you get? You get 3 omega component and omega component. 3 omega component at the upper and lower arm are of opposite phase relationship. So VL minus VU adds up to create 3 omega at the output. Okay, and then okay, so if there is 3 omega component at the output, there is 3 omega current, and 3 omega current through the upper and lower arms create 4 omega capacitor voltage ripple. Do you get it? Yeah, so 3 omega current at the output splits equally. 3 omega current creates 4 omega capacitor voltage and keeps and so on. So 2, 4, so 5 will be produced, 6, 8, everything. All even harmonics will be produced in the, even harmonic currents will be produced in circulating current, and all odd harmonic voltages will be produced at output. But the thing is, we choose capacitor voltages in such a way that this 2 omega ripple is very small. That means even when I have a large 2 omega current due to this power component, to reflect it at the pure DC submodule capacitor voltage, I need 2 omega current, right? That 2 omega current produces 2 omega capacitor voltage ripple. That 2 omega current does not produce so much of a 2 omega ripple because capacitor is very big. We choose a capacitor so that it is big enough, it doesn't produce appreciable second harmonic voltage profile in Vc. So we did this. Now carrier phase shifts. So for carrier phase shifts, we have this. Okay. Okay. So what we want to see here is that I will rub all this off. I'll rub this off. Rub this off. Okay, what do we have now? Yes, carrier phase shifts. Now imagine that all submodules receive the same carriers. Okay, so what do I do by sine triangle PWM? I have a sine wave and I have a carrier. I have a carrier which goes up and down like this. Right? So, and then when the sine wave is more than the triangle, we create a pulse. When it is less, we don't switch the module on. Now, if you have the same carriers provided to each of the submodules, don't you think that they will all be inserted at the same time? What I mean is, I have a triangle, I have a triangle here, and I have a sine wave here. I have a triangle here, and I have a sine wave here. So if all the triangles are same and all the sine waves are same, they will all the submodules will be inserted at the same time, right? Together. We don't. So what happen if we do that? We will create. So either all of them are inserted or all of them are bypassed. We have only 2 levels now. Do you think? Do you agree? If you give the same carrier and same sine wave to every submodule, then all of them will be inserted together. All of them will be bypassed together. So when all of them are inserted, for example, in the upper arm, we have VDC by 2 minus 4 VC minus VDC by 2, one level. When all of them are bypassed, we have plus VDC by 2, two levels only. Do you see? So we shouldn't give the same carrier to each submodule. We should give a different carrier to different submodules so that for the same average voltage level, each one of them is inserted at a different instant. How does that help us? What do we need actually? When we have voltage level here, we want say the PWM to switch between. Suppose this is suppose this is a wave and this is a wave, and net VU wave is like this. Suppose we want to produce a voltage level here. Maybe we want to switch between 3 and 4 submodules or 2 and 3 submodules, right? We want the net number of modules to be inserted in upper amp to be switching between 2 or 3. So so if you have 4 submodules, in total in the upper arm, and we want switching between 2 or 3 submodules, we want any 2 of them. In fact, it's not the same 2. 2 out of these 4 or 3 out of this 4 should be inserted. So what happens is, suppose I have 4 submodules here like that, and this gets inserted and this gets inserted now. After some time, what will happen? This will go out and this will get inserted for the same 2 levels. After some more time, this will go out, this will get inserted for the same 2 submodules. If you wanted 3 submodules, when these 2 are inserted, maybe this inserts, so we get 2 to 3, and again we want 2, so this goes off. Do you follow? So 2 and then 3 and then 2 and then maybe 3 and then maybe 2. Do you see? So that's what's happening. So to make that happen, we want different carriers to each of these submodules. What do you mean by different carriers? Suppose that we will see that. We will see in this way. Oh my God. Better take. So the number of modules, whether it is 2 or 3, it should also depend upon the level of this sine wave, right? If it was here, it should be only 1 and 2. If it is here 2 and 3, there 3 and 4. So it should also depend on the level of the modulating signal. So if you carefully look at this waveform, if you can see my cursor, this violet modulating signal is more than how many carriers at this instant? Is more than 2 carriers, isn't it? Do you see? And it is less than 2 carriers. So 2 modules are inserted, 2 modules are bypassed. Now let me move a little bit to the right. Now it is bigger than how many carriers? Here? 3. It is bigger than 3 carriers, right? And it is less than 1 carrier. So what do you think will happen between this and this? It will switch between 2 and 3. Do you see? 2 and 3. But let's go further. So here the modulating signal is more than the green and the red carrier. Here it is bigger than the green, red and the blue carrier. Okay, so 2 and 3. If I go further right, it is bigger than blue and red carrier. Huh?
Can you zoom in a little bit more?
Yeah.
Yeah.
Okay, so here it is bigger than green and yellow carrier. Here it is bigger than green and red carrier. And then next it is bigger than blue and red carrier, and then the red goes off, it is bigger than blue and yellow carrier, and then we have yellow and green again. So we started with what? We started with red and green, and then we have blue and red, and then we have yellow and blue, and then we have green and yellow. So there are 2 different pairs every time. Why is that happening? What do you see? There are 2 different pairs of carriers every time where we want 2 modules to be inserted. So if I go back again here, it is bigger than red and green. Here it's bigger than blue and red. So what happens to green? Green goes out. Green goes out of out and above modulating signal. And then what comes in? Blue comes in. Blue was bigger here. but blue comes in here. Do you see? Why is this happening really? Because the carriers are phase shifted. So suppose the first rising carrier was blue, yellow rises next, green rises little further later, red rises little further later. Okay. So the period of modulating signal being bigger than 2 carriers only captures any 2 of the 4 carrier waves, and there are 2 different carriers every time that happens. So the way in which the phase shifts are designed to get this to be happening is that so before that, so we have this. So what if the modulating signal was very high? What if the modulating signal was here? Then it would be bigger than all 4 carriers, right? So that is what will happen when modulating signal goes high. We want all 4 modules to be inserted to create a big VU. So it also depends on modulating signal level, how many carriers are inserted, and if it was here and if it was constant, it will be switching between 4 and 3. 4 and 3. So if the modulating signal goes bigger, it will switch between the adjacent 2 levels. We know that. What else do we need? How to design the carrier phase shifts? So if you look at the simulation file here, see the carriers are phase shifted like that. There are 360 degrees totally, and then it's phase shifted by 1/8 of 360, 2/8 of 360, 4/8 of 360, 6/8 of 460 for the upper arm, and 1/8 of 360 like that. So this is done to so that we get the maximum number of levels possible in VU. Yes.
So the fact, I understand that you want to phase shift the carrier waveforms so that you can get the different levels.
Yes.
But is there any other significance to the fact that, say, like submodules 2 and 3 are on, and then submodules 3 and 4 are on?
Yeah. So it's a very good point. Doesn't matter whether we have different 2 submodules on. That's the question, right? For when we want 2 submodules to be inserted, doesn't matter if 1 and 2 is always on, or should we switch between 1 and 2, 2 and 3, 3 and 4, right? You know what? The carrier phase shifts that we give to the submodules affect which submodules are turned on, but we don't let that decide which 2 submodules are on. Do you know what we do? We do capacitor sorting and balancing to decide which 2 submodules are on. So what we do is we find out the net number of submodules that need to be on. If the carriers decide that 2 submodules need to be on, what I will do is I will take that number 2 and then I will see which capacitors are lowest in charge. And I will insert those 2 capacitors provided the current direction is so as to charge the capacitor.
If the carrier waveforms are fixed triangle waves,
Uh-huh.
how do you choose to turn on?
Yeah. So the triangle waves gives us an output number, right? It says 2, 3, 4. I take that number and give it to this block. See this yellow block here? That takes the sum of the pulses from the 4 carrier comparisons, and then it decides which capacitor to insert. So here I have directly given these pulses to the submodules here. Now we will definitely see something. We will see that maybe next class or something. But if it is redistributed through this block, then we get perfect balanced capacitor voltages. So we have done this maybe. So the way we phase shift carriers, we get maximum number of levels. For example, in the limits, if all carriers were 0 degree phase shifted, we get only 2 levels. If there was some other phase shift, maybe we get an in-between level, but the optimum phase shift is this, equidistant carriers, so that we get all levels. And the levels depend upon the level of the modulating signal. If it's very high, it's 4 and 3, little bit low 2 and like that. So we did this. And effective output frequency, we didn't do it. Maybe we can do it next class. Next class, we should all bring laptops, it seems, because we'll be doing something here. Okay. Yeah. Thank you.
So does sorting mean that you don't need to do second harmonic suppression in the modulation?
Second harmonic suppression only results in higher capacitor voltage